Okay, so welcome everyone to this week's eCHT. I see a number of old familiar names here, as well as quite a number of first-time visitors. That's great. Welcome. After the talk today, we are going to experiment with an online coffee hour. We think we have a way of using Zoom to kind of facilitate small group conversations. So if you would like to stick around for half an hour or so afterwards, you're welcome to do so. But if you've got other places to be, things to do, by all means, no expectation there. Okay. So today we are going to hear from Mark Behrens, who will be telling us about C2 equivariant stable stems.
Hi, y'all. Really, honestly, I mean, to be totally honest with you, a lot of what I'm going to be telling you about is really, for the past couple of years, I've been watching with bated interest the computations of Dan Isaacson and his collaborators. Isaacson. Hold on, my daughter. Hey, Kelsey. I'm getting a seminar right now. They can hear you. Okay, so okay. Sorry. So Dan Isaacson and Dan Duggar. So Duggar Isaacson. So I'm just going to list a bunch of names. And then Ava Belmont and Bert Guyot. Dan, am I missing anybody here? This is a combination of R motivic and C2 equivariant computations.
Sure. I mean, lots of people. Maybe we don't have to write them all down, but
I know there's a lot of more historical people to mention too. But yeah. I'm talking about this sort of recent push in data that this group of people have been doing.
I think Hannah Kong also may.
Oh, Hannah Kong, right?
Included.
Very good. Okay, great. So I've been looking at this data, and I'm going to be spending a lot of time showing you the data. And basically, I just have been thinking about it and trying to understand it. And unlike, really these R motivic and C2 equivariant computations, they are bi-graded homotopy groups, which is very similar to the motivic story. The complex motivic story. But the complex motivic story, everything is like a polynomial algebra over tau. And so it's pretty easy to understand the data from the point of view of like a two-dimensional chart. But the problem with this data is it's kind of inherently three-dimensional in nature. And so it's a lot to parse. And I've just been trying to understand it. And I thought I'd spend the time just kind of going through some things and my attempts to understand it and how it relates to classical computations, et cetera, et cetera. Okay, so the two things that I'm interested in mainly are so everything is at the prime 2, and we've got the and I'm interested in the real motivic stable homotopy groups of spheres and the C2 equivariant stable homotopy groups of spheres. And I suppose in one of these talks, what I should really start by doing is telling you, oh, what are these things? What is this real motivic stuff? What is this C2 equivariant stuff? But to be perfectly honest with you, I'm not going to do that because I'm assuming that this being this equivariant, or this electronic computational homotopy theory seminar, that a lot of you guys, if you're here, you probably already know what I'm talking about, or you probably wouldn't be here. So, so if you'll excuse me, I'm just going to jump into talking about the computations. Okay. So, so what are the tools? What are the tools that these folks I mentioned have been using? So as Dan mentioned, there are, especially these C2 equivariant, though there's been a lot of work in motivic too. I can't go into all the names involved, but I should at least mention on the C2 equivariant front, a lot of classical work had been done by folks like Landweber and Araki and Inoue. Hopefully I'm spelling the name right. probably not looking at it. Anyway, there's been a lot of classical computations of these things, but this sort of new wave involves using the atom spectral sequence. So equivariant atom spectral sequence and motivic atom spectral sequence. I'll just call all these things atom spectral sequence, okay? Based on mod 2 cohomology, appropriate versions of mod 2 cohomology in each of these categories. And this is all based upon an understanding of the Steenrod algebra in these contexts. So there's the real motivic Steenrod algebra, and there's the C2 equivariant Steenrod algebra, and these are bigraded. So I'm just going to do the equivariant notation of putting a fancy star for the bigraded versions, and these things have been computed. This in general by Voivodsky, and this by Hu and Krish. And the atom spectral sequence is based on computing ext of these things, okay? So just to establish some quick notation, we have two versions of regular cohomology that we're working with. There's the mod, this will all be mod 2 cohomology. So there's like the real motivic version and the C2 equivariant version. And the coefficients for the real motivic one is going to be F2 adjoin two guys, tau and rho. And then this over here, this is going to be an F2 on two guys, U and A. Okay, but then there's an additional summand, F2 adjoin U A mod U infinity A infinity. And there's a functor from the real motivic to the C2 equivariant category called Betty realization, which I'll simply write like absolute values. And the Betty realization will take the complex points of the variety defined over R and give you a C2 equivariant gadget. And so that provides a homomorphism from here to here, and it provides a homomorphism from here to here and a homomorphism from here to here. And the realization of tau is U, and the realization of rho is A. Okay, and this guy A is a very familiar guy. This is the inclusion of S0 into the sign representation. So A has a representation grading. If I put things such that it lands in S0, A has a representation grading of minus sigma. Or if you think about it as a bigraded thing, so these bigraded guys, we use the first star is used to denote the dimension, and the second is like the weight. And so and so in this bigraded notation, A has bi degree -1 to indicate that it's dimension -1 and -1 copy of the sign representation. Okay, right, and let's just launch into this. So let me just mention the structure of these Steenrod algebras while I'm at it, so I'll need to refer to that. So so this guy over here is going to have a structure. It's generated as an algebra by, well, let's talk about the structure of the, so what I mean here is I really mean the duals. Let's talk about the dual Steenrod algebra. So this will be like HR star adjoin Xi1, Xi's and tau i's. But the only twist here is that tau I squared, so the twist here is we're at the prime 2, but we've got tau i's, and the Xi's are playing the role of the old Xi squareds, but tau I squared has this funky relation. tau I squared equals I eta r of u times ci plus tau a times tau naught. So tau ci plus 1, tau I plus 1. Did I get that right? And here, eta r of u. So it's a Hopf algebroid. So the right unit is of u is u plus a tau naught. Okay, and then this sorry. Oh,
sorry, can I ask you? With
yeah.
with the motivic string algebra.
Yeah.
So what is the u and a here?
Oh, my bad. Thank you, Nikolai. So I think we all make this mistake where we'll. So for me, I think I'm going to. Because of this here, I'm going to confuse the two. Okay. So when I'm working in the real motivic context, I might accidentally use u and a to refer to tau and rho. And I think people that come at this from the motivic standpoint will mistakenly call u and a tau and rho in the C2 equivariant. So here, I mean eta r of tau is tau plus, well, okay, everywhere I wrote let's just keep this. So for me, I'll say that u equals tau and a equals rho, and you'll know which one is which as to whether we're in the motivic or the C2 equivariant context. Okay, and this C2 equivariant guy is similar, but we just have to tensor it up. Okay, so then we have associated atom spectral sequences associated to these that will be like x'd over the appropriate variant of the Steenrod algebra. So here dash is either C2 or R. And then the appropriate variants of homology converging to the appropriate variants of homotopy. And these are the computations that I want to talk about. Okay, so let me show you some of these pictures real quick. So here so first I'd like to pull up this recent paper of Belmont and Isaacson. So they have charts. And so let's try and understand what these charts look like, because they're a little bewildering at first. So we're looking at the E2 page of the atom spectral sequence here. So what does this mean? Let me try and do like a split screen here. So what does this mean? So in these charts, the way that I like to visualize it, I like to visualize the bigraded homotopy groups like a grid. And so like if I was doing the, so in this direction here, you have dimension. So if we're looking at pi ij. This is like the I, and this is like the J. Okay, and what they have here are things that are they do things by Milnor-Witt degree, or now it's called co-weight. So the co-weights are the diagonals. So we're looking at, so everything in this diagonal is co-weight 0. Everything in the next diagonal of slope 1 is co-weight 1, and everything in this diagonal is co-weight 2. Etc. Etc. Okay, and so if we take a look at these pictures here, you'll see there is a shoot, I didn't think about how I was going to write on this. Well, let me just, can you see my my cursor, guys? Yeah, okay, great. So so this class over here is H1. So it's the guy detected by C1, and it's in wait, right, sorry, this is uh, right, okay, so this is H1 over here, and so you can see and you can see you have the powers. So you see powers of H1 here, and the red lines are powers of A. So you have these like A towers coming off this thing. And then you have this class H0 over here, which is detected by tau 0. And then there's this real funny thing that you have to get used to, which is that 2 is not equal to H0, or is not detected by H0. Rather, 2 is detected by H0 plus H1A. Okay, so you have to sort of know some of this multiplicative structure to read off the actual groups. Okay, so this is happening in coate 0. This is happening, you have this sort of picture in coate 1. I'm just going to show you some of these pictures. Okay, and the question is, how can we kind of parse these pictures? How can we relate what's happening in these pictures across these different coates to what's happening in the classical equivariant stable stems? It's a little confusing. And these charts get rather elaborate. They're really quite amazing. Just sort of scroll through them so you can sort of see them in their magnificence. But how can we relate this to ordinary things that we're used to in ordinary stable homotopy groups? And let me say, by the way, one little funny thing, which is that the Adams differentials change coate. So if you want to use these charts to compute Adams differentials, and they do compute Adams differentials in this paper, by the way, but the Adams differentials decrease the coate. So you have to think about differentials coming from this page over here to this page, okay? Alrighty, so what can we do? So I wanna highlight a couple of things that you will notice if you look at these charts. Okay, the first is that there's a kind of a U periodicity that happens through a certain range. So to illustrate this, I'm going to, but the U periodicity depends. It'll go by powers of 2. So U will multiply U. So A is in coate 0, so we're looking at A towers here. But U is not even an element of the stable stems. Remember, or it is not an element of X either. It had a non-trivial right unit. But nevertheless, in a way similar, so let me go back. To something. So something that I have in recent work with Jay Shaw. We show that that if you take the cofiber of A, it has a tau self-map, or it has a U self-map. And more generally, if you take the cofiber of A to the I, it has a U to the 2 to the J self-map, where J is some appropriate number relative to I. We have specific numbers for these. And this is related to something that was observed even way back in the work of Landweber in the equivariant context, which is a manifestation of James periodicity that happens within these things. But I just want to show you this in the context of these pictures. So if you look at this little piece that you see in coate 1, let's take a look at, like, let's add 4 to this. So let's look at coate 5. In coate 5, you'll see this piece say the same over here, but then you'll see a little extra stuff over here. And then if we go to coate 9, you'll again see that little pattern here and that same pattern here, and then some more stuff, okay? So there is a certain sense in which you can, much like in the context of V1 periodicity or something like that, where you can sort of, where you can think about what the U periodicity is of every element, and you can talk about inverting U. And our main result, me and Jay Shaw, says that the C2 equivariant stable stems are what you get when you take the real motivic stable stems you invert this U, so you enact this U periodicity. So I'll explain that in more context from these charts. But I want to highlight that right at the beginning, that we have this kind of phenomenon going on. There's another kind of phenomenon that I want to talk about, which is A divisibility and A periodicity. So let me go over here and say a couple quick things. So this requires us to talk about the equivariant. So in the C2 equivariant context, you have X and you have you have the homotopy completion. This is Greenlease in May. And you have EC2 twiddle over here. And then, so this is something that I'll write as X upper H for the homotopy completion. This is something I'll write as X upper phi, because this is a guy whose geometric fixed points, or whose fixed points are the geometric fixed points. And then what belongs over here is something called XT, and that's because its C2 fixed points is the Tate spectrum. But in the context of this element A, this guy XH is the completion at this element A. This guy X phi is the localization as you invert A, and this guy over here is what you get when you take X and you complete it at A, and then you invert. So in this sense, the Greenlease-May square is an A arithmetic square. And the reason why I want to bring this up is that so it turns out that so I believe this is Bachmann, the A inverted real motivic stable stems are isomorphic to the A inverted C2 equivariant stable stems. And then and the let's see here, and moreover, the A inverted stable stems are the homotopy groups of the geometric fixed points. But the geometric fixed point of a suspension spectrum is a suspension spectrum, and so that'll just be a copy of the stable homotopy groups of spheres. And so what I want to highlight to you when we look at these charts over here is that these A towers that you see, so this looks like A towers on powers of H1, but if I use the A towers to move me over into degree 0, I in fact get one A tower for every power of H0. So these A towers here are what's contributing to a polynomial algebra on H0 in the stable stems. Here, this A tower on H2 is actually corresponding to H1 in the stable stems. This A tower on H2 squared corresponds to H1 squared in the stable stems. And then these three A towers over here, these correspond, this is H2, H0 H2, and H0 squared H2 in the stable stems. So in this way, you're getting like a sort of weird shifted copy of the stable stems sitting aside of these R motivic charts. And something similar will happen in the C2 charts, but we'll see that the origins of the A towers are a little different potentially. Okay, right. So now, and then the other thing I want to highlight to you is something. Well, I think I'll get to the A divisibility in a little bit. So let me let me first concentrate on some theory, and then I can say it in the context of these pictures. Okay. So what I would like to do at this point is I would like to make a brief digression to remind you about the Seagull conjecture and the Mahal invariant, and then I'd like to tell you how to read off these, how to relate the real motivic stable stems, the C2 equivariant stable stems, and the homotopy groups of stunted projective spaces. So let's first recall the Mahal invariant and the Seagull conjecture. So Seagull conjecture. So for a general group G, the Seagull conjecture says that if you take the G equivariant sphere spectrum and complete it at the augmentation ideal of the Burnside ring, then this is equivalent to the homotopy completion of the sphere spectrum. So this homotopy completion is an algebraic completion. However, if we're working in the two complete context, then the C2 equivariant sphere spectrum is already complete with respect to the augmentation ideal. So C2 equivariantly, the Seagull conjecture is saying that the C2 equivariant sphere is equivalent to its homotopy completion. Okay. And that then, if I expand out this diagram, this Tate diagram, and originally this was Lin's theorem, by the way. So this was first proved by Lin. And in the context of this square, what we're saying is this is equivalent to this, and this was proven by means of the fact that this is equivalent to this. Okay, and so so that tells us that that this Tate spectrum is equivalent to this geometric fixed point guy. So I can take fixed points of this. So the geometric fixed points of the sphere, which is just the sphere, is then equivalent to the C2 equivariant Tate spectrum. And this thing has a classical model, which is given by the suspension spectrum of P minus infinity, infinity. Okay. Alrighty, and so you have this weird, you have this weird thing that the C2, you know, that the sphere is equivalent to a suspension of P minus infinity, infinity. And if you don't know what I mean by this P minus infinity, infinity, here what I mean here is if you take RPN and take the Thom spectrum with respect to S times the canonical bundle, this thing will be it's actually homeomorphic to RPN plus S mod RPN or S minus 1. And then this thing we will define P S N plus S to be that. And so in this way, because I can make Thom spectra when S is negative, if I just have a virtual bundle, I can make a Thom spectrum. So that allows us to make sense of this even when S is less than 0. And so then I can define P minus infinity, infinity to be the inverse limit of the co-limit. If you like, it's just the inverse limit over I of the P minus I infinity, where of course P minus I infinity is a co-limit of P minus IJs. Okay, so how does the, so what is the Mahal invariant? There's an Atiyah-Hirzebruch spectral sequence. There's an Atiyah-Hirzebruch spectral sequence that starts with a bunch of copies of the stable homotopy groups of Sn for N and Z, one for every cell of P minus infinity, infinity, and it converges to the homotopy groups of P minus infinity, infinity, which is, well, if suspension P minus infinity, infinity is the sphere, then this is S minus 1. And the way the Mahal invariant works is that if you take an element alpha in the stable homotopy groups of spheres, you ask for an element beta in the stable homotopy groups of spheres that detects alpha in this spectral sequence. And then we say that beta is the Mahal invariant of alpha. As such, the Mahal invariant is not well defined, but we're not going to worry about that. And Bruner and Greenlease observe that the Mahal invariant has another interpretation. So now I'd like to come to the C2 equivariance charts for a second. So I'm going to pull up. So these charts that I'm going to show you are charts of Dan Isaacson and Bert Guyot, and they are not released to the general public, but I've gotten their permission to show you these charts and to show you some
screenshots.
Yes. Hold on here. I'm sorry?
I was joking. I said no screenshots.
Oh, no screenshots. Yes. Yes, but these are let me see if I lost them over here. Let me just pull them up for you guys once I locate them. Okay. So probably I should do these side by side so you can compare them as at the beginning. Okay. So let's try a side by side comparison here. So of course I'm just showing you the E2 term. Oh, I have to separate them. So I'm just showing you the E2 term of the atom spectral sequence, but I feel like it gives a feel of what's going on. And later I'll make some comments about algebraic versions of some things that I'm going to say if I have time. So so here, oops, I need to change how we look at this here. So this page display, I want a single page scrolling. Okay, and I need to make this bigger. Sorry, my dog is barking. Petey hush, okay. All right, let me just make this bigger for you guys. And so let's take a look over here, this co-weight zero business. So this co-weight zero picture is available in another paper of Isaacson, of Bert Guyot and Dan Isaacson's. And here in co-weight zero, you see just this H0 tower over here and this H1 tower with these A guys. But here what you see is you see an H0 tower, and then you see this H1 tower and these A guys. But then look at all this other stuff you see. All this other stuff is like contributions from, I don't know if I said it, but let me just say it over here. This guy, when we look at the right. So when we look at the homotopy, when we look at these homotopy groups, this extra piece here is called the negative cone. This negative cone, and so the oops, I need to go back over here. So all this stuff over here are contributions from the negative cone. And then something remarkable happens in the E infinity. Let's see, can I pull that up real quick? Do I have that available? Oh, I think I do over here. So let me pull up the this Guyot Isaacson paper that talks about this phenomenon. So in the atom spectral sequence, there are hidden A extensions that go from these guys over, and these hidden A extensions give rise to extra A divisibility. Okay, and the way the Mahal invariant works is so let me try and explain this with this picture over here. From the point of view of these charts. So the way the Mahal invariant works is that an equivariant perspective is that the C2 equivariant stable stems, if you invert A, these things are isomorphic to the classical stable stems. And so you take an alpha in here, right? And then what you do is you look at it where you didn't invert A. And so then this alpha is going to be detected on an A tower, right? On one of these A towers. And then you ask yourself, where is the origin of the A tower? So like if I look over here, like if I take a look at H naught to the fourth, H naught to the fourth is detected by this A tower. And then you ask, where does that A tower start? And in homotopy, with this hidden extension, it goes back all the way over here to this element, this element over here in degree 7. And then what you do, once you get the origin of the A tower, so here you've got an alpha, and so you have your alpha. So alpha is an element in the A inverted guy. And so then we're going to get, what we're going to do is we're going to represent it by an element alpha twiddle in here. And this element alpha twiddle is going to have the power that the property that alpha twiddle is not equal to A times something else. And then if it's not equal to A times something else, it'll have a non-trivial image in the cofiber of A. However, the cofiber of A is the same thing as C2 plus. So this is actually just another copy of the stable homotopy, the non-equivariant stable homotopy groups of spheres. So this guy will map over to an element beta, and beta will be the Mahal invariant of alpha. So this story of where do these A towers, we know the A towers are indexed by the non-equivariant stable stems, but the story of where these A towers originate is really a story of what are the Mahal invariants of all these elements, okay? So I wanted to bring that into the discussion quickly. And now what I want to do is I also want to highlight the relationship of these charts and my work with J. My theorem with J. Shah. So I acknowledge that I'm just showing you ext pictures rather than pictures of the stable stems, but I feel like this sort of illustrates the phenomenon. So let's take a look at co-weight 1. In co-weight 1, motivically, you only see this little chunk. So C2 equivariantly, you see this little chunk, but you see all this other mess. And I'm saying that if you go far enough out by like u to a high enough power of 2, you'll get this stuff in increasing range. So let's take a look at what the Belmont-Isaacson charts look like when we add a large power of 2 to this. So let's see, do they go out to co-weight 17? And they do, okay? So now we can zoom this out, and now this is looking just like that. So this is where you're seeing the phenomenon that by inverting U, you get the C2 equivariant charts from the R motivic charts. Now there's a bit of a funny business here. The funny business here is you might say, whoa, how is this inverting U giving these extra A divisibility when we look over here in co-weight 0? Why do we only have this small A, this A divisibility, but why do we get this? Remember, you have to remember these hidden extensions. Why in the C2 equivariant do we get this extra A divisibility here? And that's this kind of remarkable thing that by inverting U, you end up reconstructing these A towers. So let me explain what I mean by that, okay? So probably the most efficient way for me to do that is to, instead think about it through the following lens. Instead of thinking about the Greenleaf-May square, I'm going to think about the cofiber sequence EC2 plus goes to sphere, goes to EC2 twiddle over here. And so that cofiber sequence is assembled, and there's a sort of, so this is, so what we're doing here is what we're really doing is we're taking sphere and we're going to sphere where we invert A. And then the next term here would be something that you might be tempted to call sphere mod A infinity, which is the cofiber. And so this term over here is sigma inverse of sphere mod A infinity. Sorry, sigma inverse, yes, of sphere mod A infinity. So you could think about this EC2 plus as being that guy. And then, so you could do this both C2 equivariantly, and you could do this motivically. So let's do this. So let me write the motivic one. So here you'd have the motivic sphere. I'll write mod rho infinity. And here you have the, so this is like the C2 sphere. Here's like the real motivic sphere. And then here you have the sphere where you invert rho. So we know that this is an equivalence. And so the real question is, what is the relationship between these two guys? And so my theorem with J. Shaw very specifically is saying that S mod A infinity is S mod rho infinity when you invert tau. Okay, so so what's happening here is that what's actually happening when we're building up the A towers over here is what we should do is we should look at infinite A divisible towers over here, A divisible towers, but then there's this map from S adjoin A inverse mapping to here, okay, and the kernel of that map is producing the A towers. So so what I tried to draw here is a copy of F2 adjoin A mod A infinity. And what I have over here is a copy of F2 adjoin A plus or minus. And the way you should think about it is it's like that this is mapping to this. And then what it's leaving behind is an A tower. And so in this way, you can understand these Mahal invariants. These Mahal invariants are sort of secretly encoded in this real motivic data. Let me explain it in the context of this element over here. Let's look at let me find a good one here. Let's focus in on this tower in coweight 2. So this H2 squared guy. Well, no, let's go back over here. So let's take a look at this tower over here, but then let's compare to the C2 equivariance story. So we get this. The extra A divisibility goes in like a jagged line over here. But now if I look at the real motivic data, so I'm going to look, so here I'm looking in coweight 0, but there's a little degree shift having to do with the long exact sequence, where I have to look at A divisible towers in coweight 1 below. So I have to look at A divisible towers in the C2 equivariant in coweight -1. Now fortunately that appears here in these charts, or sorry, where is, what am I trying to find? Ah, sorry, I need to think about the mod A infinity version. So let's ignore this for the moment. Let's take a look here, because you have to do this in sphere mod A infinity. So I'm going to look in coweight 3, and I see this little jagged pattern here start to form, and I get some A divisibility here. But if I go to coweight 7, I get increased A divisibility, and it starts to make more of that jagged pattern. And then I go to coweight 15, and I get even more of this jagged pattern. and even more A divisibility. And the claim is that in the limit in degree -1 of a sphere mod A infinity, you'll get infinite A divisibility together with this jagged pattern. And then that will work in concert with the A inverted guy to give the desired pattern in coweight 0 for the C2 equivariant thing. Now, I'm not advertising this as an effective way of computing Mahal invariance. It's highly ineffective because you have to know information in arbitrarily high coweights in order to be able to interpolate it to get what happens, in the limit, if you will. But I still find this to be interesting. Okay, in the remaining time I have left, I would like to explain a process by which you can read off a different way in which to read off the C2 equivariant stable stems in terms of the homotopy groups of various stunted projective spaces. Okay. So I'm again going to return to this Greenleaf-May square. So we have here pi ij of the sphere, and the Greenleaf-May square says that I should map this to so pi ij c2 of this homotopy complete sphere. Sorry, there's no C2 there. And then I should map this out to pi j sphere mod A infinity, or A inverse. And then this goes to pi ij of this Tate thing. And then, of course, I have this other term, which is pi ij of EC2 . Okay, and I'd like to just focus on, so this is just an isomorphism. This is equals. However, this also turns out to be an isomorphism because of the Seagull conjecture, and equivalently, this is an isomorphism. Okay, now what I would like to do is I'd like to take a look at, so let's try and decode what this is. So this is like equivariant home. These are maps from, well, what are we looking at here? This is Si minus J plus J sigma mapping into EC2 plus C2 equivariant maps. And so this is otherwise known as maps from Si minus J into EC2 plus smash S minus J sigma, bringing that over to the other side. And so this is the same thing as, because C2 is acting trivially on the Si minus J, this is going, well, I guess this is equal to pi I minus J of the C2 fixed points of this spectrum. And then the Adams isomorphism is going to kick in. And this will be pi I minus J of, so this is a model for, so this will be the homotopy orbits. And this is a model for P minus J infinity. So, so these homotopy groups that we're looking at over here are really the homotopy groups. This is really pi I minus J of P minus J infinity. Okay, and this guy over here, we just said that this is, well, this is what you get when you just write down the answer, because I don't have time to really derive this. So this is pi I minus j of sigma p minus infinity infinity. This is that Tate guy. And then the next term in the cofiber sequence would be pi I minus j of pi I minus j of sigma p minus j infinity. And this is the truncation where you mod out so this guy over here is the pi I minus j. Of course, you could also just read this off from here and use a Tia duality. But this is going to be pi I minus j of suspension p minus infinity minus j minus 1. And so this cofiber sequence that we are looking at up here is really a cofiber sequence that comes from thinking about the homotopy groups of the stunted projective spaces and their relationship to the homotopy groups of p minus infinity infinity. Okay? So with that in mind, we should be able, so with that in mind, that of course we know that this is just isomorphic to pi I minus j of the sphere. So what this tells us is we should be able to read off pi star star C2 from the stable homotopy groups of spheres together with the Mahal invariant information. And the homotopy groups of these stunted projective spaces. Okay, so let's look at some data, and that will finish my seminar, it looks like. So this is Mahal's metastable homotopy groups of spheres. And what we're looking at here is he computed the atom spectral sequence for all of the stunted projective spaces. He computed the first 28 stems of all the stunted projective spaces. So we're looking at pk infinity, and here he's divided k into congruence classes mod 16. Now, these aren't actual atoms charts. In fact, this isn't even a picture of the atoms E2 term. Rather, it's what he calls a pre-spectral sequence. So it's almost the atoms E2 term, but you have to run like an additional differential to get the atoms E2 term. And those depend additionally on the congruence classes. But I'm not going to confuse you with that. I want you to just pretend as if these are pictures of atom spectral sequences for pk infinity for the moment. Okay, and so here we're looking at so I want to look at p minus 1 infinity, and so because minus 1 is 15 mod 16, it's going to look like this. So here are the stems 0, 1, 2, 3, 4, 5, 6, 7, and then they go on to 15, 16, 17. So he has them superimposed on each other. And so what you do is when you look at pi 0, you see, so this class I circled here, I circled it because 1 in the stable homotopy groups of spheres, in the stable homotopy groups of S minus 1 is detected on the bottom cell by this class. Then if we go to p minus 2 infinity, here's p minus 2 infinity, here you get 1 and H0 is detected. And then you go to p minus 3 infinity, and you get 1 H0, H0 squared, and H1. So this is the way in which p minus infinity infinity becomes the sphere spectrum, because slowly p minus n infinity starts to look like a copy of the sphere on the minus 1 cell. So I'm going to sort of do this like an animation. You can see it kind of growing, a copy of what looks like x to the sphere. You see how that, you see that grow? So that's the process by which, as you let n n go to infinity, p minus n infinity starts to look like the sphere. And so this is really what we're interested in when we're talking about looking at these Mahal invariants. And this story that I told you over here, what it tells you is it tells you that you can recover these you can recover these C2 equivariant homotopy groups from these charts that I'm showing you together with the Mahal invariant data. So let me try to illustrate that for you guys. So now at this point, I think it's useful for me to show you a different lens. Okay, let's do it this way. So here I've enumerated the data in a slightly different way. I'm going to make it big enough for you guys to see it, hopefully. So this is a picture of the C2 equivariant stable stems, but I've indexed them instead on like this weight and dimension, okay? So here we have the dimension along this axis and the weight along this axis. And so the Milnor-Witt or the co-weight are on the diagonals, like I said before. So like if we take a look at this picture over here where you have these A towers and this A divisibility over here, that's seen as a bunch of A towers on this diagonal, and I've tried to indicate their A divisibility over here, okay? Or let's take a look at another one of these charts. So let's take a look at these C2 charts over here. Let's take a look at something, let's look at Milnor-Witt 1 over here. So you see this little pattern over here? This little pattern over here. Well, we have here's a Z mod 2, and then these two Z mod 2s over here are these two dots over here, and then here I have sorry, I'm getting lost a little bit. Oh, one Z mod 2 over here, that's this Z mod 2 over here, and this little circle with a 2, this little circle that's supposed to be a 2 written inside the circle, that's supposed to indicate these guys over here, and then a little dot with the arrow is supposed to be this little dot with the arrow. So we're just reorganizing the information. And now what I'd like to do is I'd like to go over to the Mahal charts over here. And so the Mahal charts say that if you're looking in the negative weights, we can just read them off from the stunted projective spaces. So let's take a look at the stunted projective space. Let's just take a look at, say, P2 infinity for a second. So I have to look at -2, the stunted projective space P -2. So I have to look at, sorry, no, P2, this is, oh, I see I'm running out of time here. Let me finish this up. This is weight -2, so it's P2 infinity. So I have to go to P2 infinity. So if I look at this chart here, I see I've got a Z in dimension 0. So there's a Z, that little box is a Z in dimension 0. And then this is dimension 1. I'm going over by 2. This is dimension 1. I've got a Z mod 4 over here, and that's the Z mod 4 over here. And then nothing in dimension 2. And then in dimension 3, I got a Z mod 4. That's this Z mod 4. In dimension 4, I got a Z mod 2. Here's my Z mod 2 over here. Now, the tricky thing is when you're looking in these positive weights, then you have to use the Mahal invariant information. So the Mahal invariants are both telling you where the A towers are originating, but they're also telling you, you also have to worry about the co-kernel of the map from P minus infinity to the stunted projective spaces. In other words, you have to take these pictures I'm showing you and you have to remove the Mahal invariants. So I'll illustrate that by means of taking a look at this picture over here. So this is 13 mod 16. So this is supposed to be a depiction of what's happening in weight 3. And in weight 3, we get a Z mod 2 here, which is this Z mod 2. And we get a Z mod 2 over here, which is this Z mod 2. But these guys over here don't contribute anything to the picture because they're Mahal invariants. So see, I have a 0 over here. Now this, I've got an A tower, but the A towers were accounted for separately. And then I've got a 0 over here. And I don't have anything until over here in 1, 2, 3, 4, 5, 6 in dimension 6. And in dimension 6, you see the Z mod 8 over here, which is corresponding to this Z mod 8 over here. This is probably a good place for me to end this talk.
Okay, great. I'm going to unmute everyone so we can thank him, first of all. Okay. And because we are a little bit over, I think we are going to skip the kind of the usual questions here, and also because we're going to experiment with this coffee hour. Okay.